Yeah, once again, we are going to solve some very classic problems in dynamic programming. So the problem that we are going to solve now, this is very well known as coin change. And once again, each problem in DP can be thought of as a concept. Now, in interview, you might not directly be asked that concept. You'd be asked a question, a totally unseen question, where you have to figure out how to apply that concept. Okay, so for that, our understanding of the concept should be rock solid. Okay, so this question goes as follows. It says that we have been given coins of several denominations. So what is the meaning of denomination? Like in India, if you take a look, the coin denominations are 1 rupee coin, 2 rupee coin. You don't have a 3 rupee coin, you don't have a 4 rupee coin, but then you have a 5 rupee coin, and then you have a 10 rupee coin, and then I think you also have a 20 rupee coin. So that's how the denominations work in different countries. So there are different denominations and they are given to you in form of an array. So let's say the name of the array is coins. The size of the array is m. It means there are m denominations. Okay. And those denominations are, let's say, C0, C1 till Cm minus 1. Okay. Now we have been given this array as an input, and we have also been given an integer n as an input, right? Now you can assume one thing. You can assume that we have infinite supply of each denomination. When I say infinite supply of each denomination, let's say there is a denomination of 3 rupee coin, then there are infinite coins of 3 rupee. Okay, you can assume that. Now what we have to do is, given this integer n, we want to find minimum number of coins needed to make n. What is the minimum number of coins needed to make n, as in what is the minimum number of coins which you can collect such that their sum is equals to n. And this array has been given to you, which represents the denominations that you have, and for each denomination infinite coins are there. So from each denomination you can take as many coins as possible. Is the question making sense to everyone? How many of you get that? Okay, want an example? So let's take some example. Let's say the denominations array that we have has 1, 5, and 7. Okay, so we have got infinite coins of 1 rupee, 5 rupee, and 7 rupee. And now the value of n is 9. So tell me, what is the minimum number of coins that you need to make 9? Okay, so a lot of you are saying 3. Can you also tell me what are those 3 coins which you are taking to make 9? Yeah, 7, 1, 1. So you can take a 7 rupee coin and you can take 2 units of 1 rupee coin. And if you sum them up, you will get 9. Okay. So, this problem is so classic that it is used by certain cash vending machines also. For example, you go to an ATM and let's say you want to withdraw some amount, then the ATM might try to dispense as less notes as possible. Okay, so the ATM might try to dispense as less notes as possible, and also the sum of those notes should be equal to the amount that you have entered. So this can be modeled as a real life problem. Let's say this is a very important point to understand now. Okay, so one of you is saying we have 2 options for each coin. Those 2 options, if those 2 options, let's say we assume, are either take a coin or do not take a coin, then does it make sense? Let's say you talk about 1 rupee coin. When you talk about 1 rupee coin, either I can leave it completely, or I can take it once, or I can take it twice, or I can take it thrice, or I can take it 4 times. Why? Because there are infinite supply of each denomination. It's not like you have got one unit coin of each denomination. No, it's not like that. There are infinite supply of each denomination. So whenever you are scanning this array, and let's say you are considering this element, then there are several choices for this element. First choice could be do not take it at all and then move on. Second choice could be take it once. Third choice could be take it twice. Okay. So there is a very well-known approach to this problem, which a lot of people come up with. Okay, let's take a look. You want to make 9, okay? Now, assume that this array is sorted for now. Let's make that assumption. So start from the end. When I say start from the end, try to take the largest denomination. Because when you take the largest denomination, then n decreases very fast, right? And that is what you want. You want that by taking fewest possible coins, the n should have decreased to 0. That is what you want. So he's saying first take this 7. So, okay, I took this 7. When I took this 7, the remaining amount becomes 9 minus 7, which is 2. Now you cannot take this 7 again. So you can move back to this 5. When you come to this 5, can you take this 5 for n equals to 2? Does it make sense? Yes or no? The answer is no. So again, you will move back. Now you come to this 1 and you want to make 2 rupee. So you have to take 1 rupee coin twice. That is what you do. And now it becomes 0. So this is the approach that a lot of people come up with. But start from the end and take the current coin as many times as it is possible to take, and then reduce your n, and then again take as many times as possible. This is how you keep going on. Now, a lot of you are saying it will fail. So a lot of you are saying it will fail for other kinds of input like n equals to 10. So tell me clearly, whatever algorithm I told just now, if I run it for n equals to 10, then how many coins would be taken? 4 coins. And what are those 4 coins? 7,111. Exactly. So again, you start from the end. You see that this 7 can be taken. So you take this 7, right? And now the value of n becomes 3. Can you take it again? No. So you'll move back. How about this 5? Can you take this 5 again? Or can you take this 5 at all? The answer is no, because this is 3 already. So again, you move back. Now you are here. So you'll take that 1 for 3 times. So you have gathered 4 coins. But think and say, what is the fewest number of coins that can make n equals to 10? Given this denomination, it is 2. I can just take 5 followed by another 5. So the algorithm that we just discussed, which is greedy in nature, which always takes the highest denomination and then moves back, that is not going to work. So let's move on and scrap this approach and come up with a smarter approach. So tell me, what can be done? How do we think? So don't think about DP, don't think about anything which is very, very Herculean to think of. Think of a simple recursive way. See, whenever you see questions like find minimum, find maximum, then automatically that question has a high probability of being solved using DP, right? I mean, certain times DP might not be necessary. Certain times it can be solved using simple logic like greedy. Certain times it can be solved using binary search, which will teach you. But chances are very high that it is DP. If it is DP, the first step is recursion. So think recursively. You know, here if you focus on this problem, here you don't have to tell me which coins did you pick. Like for n equals to 9, you don't have to tell me, hey, I picked 1 7 rupee coin and 2 1 rupee coin. You don't have to tell me that. You just have to tell me the answer 3, that 3 is the minimum number of coins that I picked. So if you focus on this and work your way out, you might be able to come up with a very easy recursive relation, and let us understand that. So let's keep looking. See, let's say you want to make n rupees, okay? And this is the array that you have. Okay, well, let me write a new array. This is the array that you have of size m. So that's your array starting from I equals to 0 to m minus 1. And then there are certain elements in this. Tell me, like, if you want to make n rupees, then in how many different ways can you choose your first coin? in how many different ways can you choose your first coin? If there are m options over here, in how many different ways you can choose your first coin? Tell me. In m different ways, right? See, you have got 1 rupee coin, 5 rupee coin, 7 rupee coin. So what is the in how many different ways can you pick your first coin? It could either be 1 or 5 or 7. So it depends upon the size of the array. So there are m options that I have for my very first coin. Now, just think of it. If you have taken your first coin as this, which is array 0. So you wanted to make n rupee coin. And if you take your first coin as array 0, then how much amount will be left? How much amount will be left? You wanted to make n and you took array 0. So now the amount left will be n minus array 0. Let me just write it as a. Okay, but you could have taken other decision also. That other decision could have been to take this as your first coin. If you would have taken this as your first coin, which is a1, then the remaining amount would have been n minus a1. Similarly, you can see there would be so many options. The final option would have been to take the last element. If you would have taken the last element, which is a of m minus 1, then the remaining amount would have been n minus a of m minus 1. So these are the transitions that are possible. So you can think that this is a state and you move from this state to this state if you pick this as your first coin. But if you pick this as your first coin, you move from here to here. Similarly, if you pick this as the first coin, you move from here to there. Now tell me one thing. So when you have made a decision to pick this coin or that coin or whatever as your first coin, then you have already picked one coin. Because you have already picked one coin, you should do 1 plus something. Now the question is, what should that something be? So think of it in this manner. You wanted to make n rupees, and after picking one coin, you want to make n minus a0 rupees. Now if somebody tells you what is the minimum number of coins that is required to make this much rupees, and what is the minimum number of coins that is required to make this much rupees and then that much rupees, then looks like your job is done. Now who is going to tell you? Let's say some magician. Let's say some magician tells you that, hey, the fewest number of coins that you need to make this much rupees is X. The fewest number of coins that you need to make this much rupees is Y. And the fewest number of coins that you need to make this much rupees is Z. Then using those, you can very easily solve for the fewest number of coins used to make n rupees. We can even take a very quick example here, which corresponds to all that I have said. Let's say your array is 3, 4, 7, and your n is 10. So there is a function that you call for the current value of n. Now tell me, how many transitions will happen from here? Look at the size of the array and tell. How many choices do you have for the first coin? 3 choices. And what are those 3 choices? Your first coin could either be a 3 rupee coin. If that's your first coin, you will move from f of 10 to f of 10 minus 3, which is 7. If your first coin is this, you will move from f of 10 to f of 10 minus 4, which is 6. And if your first coin is this, you will move to f of 10 minus 7, that is 3. You understand these transitions, how they are happening, right? Now, when you made this choice, then the first coin that you picked was a 3 rupee coin. When you made this choice, then the first coin that you picked was a 4 rupee coin. When you made this choice, then the first coin that you picked was a 7 rupee coin. Now, all that I'm trying to tell you is, let's say there is a magician and he tells you the fewest number of coins required to make remaining amount. That is 7. So tell me, what is the fewest number of coins that you need to make 7 rupees? Given that denomination? 1. Only 1. You can pick that coin and your job will be done. So 2 coins are needed, right? And what is the fewest number of coins needed to make 6 rupees? Given that denomination? 2, right? And what is that? You can pick 3 followed by 3. And what is the fewest number of coins required to make 3? Just 1. Pick that 3. All that I'm saying you is, you realize that for this, the answer is 1. Because you just need 1 coin to make 7 rupees given this denomination. Similarly, for this, the answer is 2. You just need 2 coins. For this, the answer is 1. So if somebody tells you this is 1, this is 2, this is 1, then you can tell me the answer for this. What is the fewest number of coins needed to make 10 rupees? Tell me. Now, what is the fewest number of coins needed to make 10 rupees? It is 2. And how did you get that 2? You got that 2 by doing 1 plus. Why did you do 1 plus? Because the moment you have made first transition, that means you have taken some coin. Which coin, I don't care, but you have taken some coin. Now, whatever is the minimum of this, and that, I can add it. So whatever is the minimum of F7, F6, F3, that can be added to 1, and that will be the value of f of 10. So does it look like, forget about magician. Why did I say magician? Say there is a function f of 10. I mean, hey, somebody tells you that what is the minimum number of coins that you need to make 7 rupees. Somebody tells you that. Now somebody tells you what is the minimum number of coins needed to make 6 rupees. What is the minimum number of coins needed to make 3 rupees? Somebody tells you that. Okay, here it is 1, here it is 2, here it is 1. So what will be the minimum number of coins needed to make 10 rupees? It will be 1 plus minimum of 1, 2, 1. You see, if you are making 7 rupees by 1 coin, then you can add 3 to it as another coin, and now you have just 2 coins using which you can make 10 rupees. Okay, so do you see that it is purely a recurrence relation? Okay, and if you want, you can even draw this recursion tree and see how the values are being returned. So let's say f of 10. From here, you will call f of 7, f of 6, and f of 3. This diagram is copy paste of that. Okay, so now what is the meaning of f of x? The meaning of f of x is it will return me fewest number of coins to make x. That is what f of x is. Is that clear? So I'm saying fewest number of coins needed to make 10 rupees is equals to 1 plus minimum of this, that. Why I'm doing 1 plus? Because the moment I made my first choice, I already took 1 coin. It was either 3 rupee coin or 4 rupee coin or 7 rupee coin. Now these are remaining amount. So if somebody tells me what is the minimum number of coins to make those amount, I can take min of those, add 1 to it, and that will be my answer. Okay. So again, you can go on from here. At f of 7, again, there can be 3 transitions, because at every stage, you can pick any of these 3 coins. Why? Because they are in infinite supply. So again, f of 7, can you tell me what will be the functions which will be called by f of 7? Very easy to say, right? Because once again, I can say that my current coin could either be a 3 rupee or 4 rupee or 7 rupee. So if my current coin is a 3 rupee coin, 7 minus 3 will be 4. If it is a 4 rupee coin, it will be this. And if it is a 7 rupee coin, it will be 0. That's how things are happening. Now again, I hope you remembered the definition of f of x. If you really remember the definition of f of x, can you tell me what should f of 0 return? What is the fewest number of coins that I need to make 0 rupees? So when n is equals to 0, just return 0. So this can be your termination condition of the code that you will write. Now again, I can draw more. So you can again see that here again, there are 3 choices. So at each node, there are 3 choices, or to generalize it, at each node, there are m choices, where m is the size of your array, where m is the number of denominations that you have. So once again, at f of 4, what will be the calls that you will make? 4 minus 3, which is 1, and 4 minus 4, which is 0. And 4 minus 7, which is minus 3, interestingly. This looks a bit itchy, right? Where the remaining amount is negative. What to do in this case? When the remaining amount is negative, but you realize it that this can happen, right? Certain times the remaining amount can become negative. Why it can become negative? Because you never know what this value is. And when you subtract an element from this, it can become negative. So you have to handle this thing in a proper manner. I'll come to that. But before that, I'll give you a very quick example to solve. So let's say we have denominations of 2, 4, 6, and we want to make 5 rupees. What is the fewest number of coins that I need to make 5 rupees here? Is it possible to make 5 rupees here? Not possible, right? So this is very important thing to realize. Now guys, let me tell you one thing. See, if you look at these edges, these are like your decision arrows. So in this particular arrow, you took a 3 rupee coin. That is the reason you moved from 10 to 7. So I'll draw it here, 3 rupee coin. In this arrow again, you took a 3 rupee coin. That is the reason you moved from 7 to 4. In this arrow, what did you take? You moved from 4 to -3. So you took a 7 rupee coin. I would say that this particular decision path is not a correct decision path, because if you are moving along this path, you cannot create the desired amount, which is 10. And furthermore, I can say there is no way I can create negative amount from positive denominations. There is no way I can create negative amount from positive denominations. So this is impossible thing. This is impossible thing. So let me erase these for now. Now, in recursion, what you do is you solve every sub problem one by one. So at f of 4, what you are trying to solve, forget about this big tree, just focus your attention on this small tree. At f of 4, you are trying to find fewest number of coins to make 4. Fewest number of coins to make 4 is dependent upon fewest number of coins to make 1, 0, and -3. Now think, what should this return? What should f of 1 ideally return from here? When you look at f of 1, you realize that, hey, given this denomination, 1 cannot be made. When you look at f of 0, you can say that because of this termination condition, I can return 0 from here. Now, these are the impossible things. So whenever you encounter impossible things, what should ideally be returned? Forget about this for now. Let's focus on this. Some of you, those who are saying return infinite, you are saying totally correct. Why you are saying totally correct? Because whatever is returned from here, you want to discard that. Why you want to discard that? Because it is not possible to make infinite amount. Correct? Now, if you are taking min of certain things, let's say min of 5 comma infinity, it will always be 5. Min of -5 comma infinity, it will always be -5. So when you are taking min of certain things, out of those things, if something is infinite, it will automatically be discarded. So what we can do is, if my function has ever been called on a negative amount, then I'll immediately return infinite from there, because returning infinite will ensure that for the computation of this thing, when min will be taken, then whatever is returned from here will automatically be kicked out. So this is very, very important point to understand. So certain times you write this kind of relationship, certain times you might write a relationship which says 1 plus max of something, something, something. And in that, if you realize that you end up on a state which is impossible state, and if you are taking max, maybe you can return minus infinite, because max of x comma minus infinite will always be x, correct? So this is again another trick that I want you guys to understand. So this is how it happens. So our first termination condition is that if the remaining amount is 0, return 0, and it makes sense, because if I go by this definition, this makes sense. Similarly, if my remaining amount is negative, then return infinite. Correct? Okay, now look at this f of 1. What will happen at this f of 1? When you look at this f of 1, again from here, you will make all those 3 calls, which is f of 1 minus 3, which is -2, f of 1 minus 4, which is -3, f of 1 minus 6, 1 minus 7, which is -6. Now all these things will return infinite, infinite, infinite. All these things will return infinite. And now again, from here, you can make sure to return another infinite, because you can just write your code in a way. I'll come to the coding part. You can write your code in a way that 1 plus integer infinite is also an infinite value that is returned to the top. So eventually what will happen from here is, when you take min of this, this, and that, it will turn out to be 0, and f of 4 will be 1 plus 0, which is 1. So you'll return 1 from here, and returning 1 makes sense, because if somebody asks you a question that what is the fewest number of coins needed to make 4, you would say 1, just take this thing. Similarly, in this manner, calls will go down, down, and down, and values will be returned. And that is how you can now imagine something will be returned from here, here, here. And f of 10, what it will do is, it will find min of those, add 1 to it, and that will be the answer of f of 10. Okay, let's look at the recursive code for this. Let's say there is a function called as min coins. This function returns something. What does it return? It returns the minimum amount needed to make n rupees. Okay, so you pass here n, correct? Now tell me, what is the first line of code that I should have? Base case, right? And what is the base case here? There are two base cases here. First, when n is 0, we return 0. And there is one more base case we just learned. If remaining amount is negative, then in order to discard the contribution of that, because we are taking min, we will return infinite, which depending on your language, you have to see, like in C, C++, there is a provision of int underscore max, which is the largest value that an integer data type possesses. Okay. Otherwise, what to do? So now comes the logic, which should be as simple as this. So whenever you are at a particular function call, let's say you are at f of n, you should be making all these calls. And how many calls will be there? Tell me. The number of calls will be equal to m, because that is the number of denominations that you have. So do I need a for loop here? I need a for loop, then only I can make those m calls, right? So I'll iterate on my coins array. So for I equals to 0, I smaller than m, I plus plus. So see, what this for loop is doing is, if this is my coins array, then my I is moving on from 0 to m minus 1. So let's say currently if my I is here, then I want to take this coin as my current coin. Now, when you take this coin as your current coin and present amount was this, then what will be the leftover amount? You take a of I and the present amount is n, then the leftover amount will be n minus a of I. I had shown it to you, right? So I can say the remaining amount will be n minus ai, correct? And you will make a function call on this. So you will call min coins method on this, correct? And also because you have taken this ai currently, so you have to add +1 to it. You add this +1 before, after, does not really matter. Okay, and you want to do this thing for all the values of I. That is the reason you have written this for loop. You want to do this for all the values of I, and for whichever value of I, you are getting the minimum possible value of this, that will lead to your answer. So what I can do is, before starting this for loop, I can have an answer variable, and I can initialize this answer to infinity. Let's say it is int underscore max to start with. And now every time what I'll do is I'll update my answer. I'll write answer equals to minimum of this expression, comma, answer. So all that is happening is, think of it in this manner. You made this call, okay, you made this call and it returned you, let's say x, it returned you x. So you have 1 plus x with you and your answer was initially infinity. So you update your answer to min of this, comma, that. And then you make this call, and then whatever is returned, using that, again, you update your answer. So this is just like, you know, scanning 10 different values or m different values and finding out their minimum. So I have initialized answer to int underscore max, and every time I'm making the call, adding 1 to it, and updating my answer if possible. Okay, now once this for loop would have been over, then think of it in this way. From this function, you would have made all these calls and you would have gotten your actual answer. So what are you waiting for? You can just return this answer. That's it. Okay, now there is one very good question that a lot of you are asking. See, I had told you in situations like these, like at f of 1, it might happen that all the children are returning infinite, infinite, infinite. So if you compute 1 plus min of int min, and store it in an integer, let's say x, what will happen? How will your computer respond to this? Theoretically, you will say, hey, 1 plus infinity is infinity, but your computer will not agree to it, because if you add 1 to maximum integer value, sorry, minimum integer value, it's not maximum, sorry, it's max, not min, max. So if you add 1 to the maximum integer value, it will lead to overflow. So there is an overflow scenario that can happen over here. So how to handle that? All that you can do is you can change the types to long. So if you change the types to long, 1 plus int underscore max, whatever it will still be greater than integer infinity, but it can be accommodated in a long. So in questions like these, this is also another point of care that you have to take in your mind. Cool. Anyways, so tell me one thing. Now, this is the code that we have, and this is the recursion tree diagram that we have. So here, n is something which defines our state. And what is n? It is the remaining amount. Now tell me something. Do you see overlapping subproblems over here? Yeah, 3, 3. So you can say, you can easily see that this f of 3 is present here also and here also. Overlapping subproblem is happening. So how do we counter overlapping subproblem? Memoization. Very good. The first step you guys have figured out. So yeah, the first thing I'll do is I'll create a memoization array. Now, what should be the dimension of this? Is this a one-dimensional problem or a two-dimensional problem? It's one-dimensional problem only. Why? Because the problem is being denoted only by one integer. The remaining amount is just one integer. It is not 2 or 3 or 4 integers. Okay. So I need a one-dimensional memoization array. And what should be the size of that array? So if you take a look, the value n will keep on reducing only. Why? Because you are always subtracting something from it. So the different values of remaining amounts that you will see in this tree, or the different values of this integer that you will see at the nodes of this tree, will be smaller than or equals to n. Now from 0 to n, there are n plus 1 integers. So it's good to initialize it to that. Right? And you can initialize all of them to some value like -1, -1, -1. Why? Because I know for sure that the fewest number of coins will never be -1. Can it ever happen that number of coins is -1? No. So I can initialize everything to -1. And now you just need to write your memoization logic over here, which is, I think, super easy thing to do. What is the first step of memoization? Base case remains as it is. No one is going to touch that. Okay. Now, after base case, the first thing that you will do is you will check in the memoization array whether answer for n is present or not. So after this line, you can write if, I hope this part is visible. You can write if mem of n not equals to -1. Okay. So what I have written is if mem of n not equals to -1, then you can just return mem of n, right? Otherwise, what you can do is you have computed actual answer in this case, because if let's say you had not solved for the amount n, then you have solved for it. And after solving for it, first store that answer in mem of n, and then go ahead and return that answer. So everything is still the same. The first part is mem check. The second part is solve and then store and then return. That's it. But do you somehow realize inside that this code will be much more optimal than the previous code? Because if you have solved for f of 3 here, if you have created a just gigantic tree for f of 3 here, you will not create that here again. It will for sure be more optimal.